Hi all, welcome to Chapter 18, Electrochemistry. Actually, welcome back. We talked about electrochemistry a little bit in the beginning of the year when we talked through Chapter 4, and we talked through a couple different types of reactions that you would see in aqueous solutions. Redox reactions were one of those types, and that's what this chapter is all about. It's all about redox reactions. So as we go into this chapter, the first half of it is all review, and that's what I want to talk about today. I want to talk about reviewing all the things that we talked about with respect to redox reactions in chapter 4. Okay, so let's talk about redox reactions and how they are used in this study of electrochemistry. So when we're talking about electrochemistry, we're talking about one of two scenarios. We're either talking about generating electricity because our reaction is spontaneous. So if we're dealing with a spontaneous chemical reaction that's going to go forward all by itself, this spontaneous chemical reaction is going to promote the movement of electrons. And as electrons move in between reactants and form products, that movement of electrons is called electricity. And when this happens by itself in a spontaneous reaction, then we can actually harness that electricity that's being generated. This is exactly what a battery is. A battery is just a system that harnesses the electrons as they flow in a spontaneous reaction. The study of electrochemistry can also be the opposite. If there is a non-spontaneous reaction that we want to happen, then we can use electricity to force that non-spontaneous chemical reaction to occur. So this might be things like resisting corrosion. As we design this whole line of products that are going to resist corrosion, basically we are manipulating these redox reactions to happen differently or happen in reverse. Electricity can be used for that. Also, a lot of electrolysis is exactly that. So if we are using electrolysis to to split water into hydrogen and oxygen, right? That's a non-spontaneous reaction. Hydrogen doesn't do that. Water doesn't split all by itself into gaseous hydrogen and oxygen, but we can use electrolysis in order to force this reaction to happen. So usually when we're talking about electrochemistry, we're talking about one of those two scenarios. We're either generating electricity through a spontaneous reaction, or we're using electricity to force a non-spontaneous reaction to go forward. Note also the indication of K in both of these. Remember that when we're talking about spontaneous and non-spontaneous reactions, those are linked to equilibrium, right? We can use equilibrium to talk about spontaneity, and we'll loop back to that later in this chapter, and we'll take a look at how equilibrium is related to spontaneity. Okay, so a couple things to review. First of all, let's review what oxidation and reduction are. You need these definitions to move forward. So when we're talking about oxidation, we're talking about the loss of electrons. Remember, Leo, the lion, goes grr. So loss of electrons is oxidation, gain of electrons is reduction. So reduction is going to be the gain of electrons. And remember, these two things always happen together. If something is being oxidized, something else must be being reduced. Electrons don't just come out of thin air, and they don't just disappear into thin air. They have to come from a source. That's the loss of electrons. And then they have to go to another source. That's the gain of electrons. Now we keep track of oxidation and reduction in by tracking oxidation states. So we'll circle back to oxidation states and review those as well. And that's the most common way we're going to look at oxidation versus reduction is through those oxidation states. Originally, when they were first studying redox reactions, they were looking at oxygen. As you can see, the whole name is based on oxygen, right? So if you have an addition of oxygen, something is going to be oxidized by that oxygen. And then reduction is defined as the reverse. But we're going to use these definitions of oxidation states instead of using the definitions of oxygen and hydrogen to define oxidation and reduction. And I have two examples here. If you have magnesium gaining or joining with oxygen into magnesium oxide, this would be an example of oxidation. And then magnesium oxide reacting with hydrogen to form solid magnesium and water. That would be an example of reduction. So let's take a look at the oxidation states. Let's review oxidation states, and then we can see how these two examples really are examples of a redox reaction where one thing is being oxidized and the other thing is being reduced. Okay, so oxidation states. Sometimes oxidation states can be charges. That is possible. Remember, the whole purpose of tracking oxidation states is to be able to track where the electrons are coming from and going to. So we're going to assign oxidation states to different things in the reaction so that we can track the path of those electrons. Now, in redox reactions, we do actually have electrons traveling. Electrons are physically moving from one thing to another thing. Sometimes that results in charges, like in the case of ions and ionic compounds. You're dealing with the path of electrons through actual charges, but sometimes you're dealing with covalent compounds. And covalent compounds don't have charges inside of them. For example, carbon dioxide. If we look at carbon dioxide, it's a covalent molecule. There are no charges inside of here. Now, there are partial charges. The oxygen's going to be partially negative, the carbon's going to be partially positive, but there are no truly complete charges within this molecule. These electrons that are involved in the molecule are distributed. They spend some of their time around carbon, they spend some of their time around oxygen, but they're not truly associated with one over the other. Those electrons are shared. A better term, those electrons are battled over by both things, right? So we're not dealing with actual charges inside this molecule. However, we are going to assign charges, pretend charges, to this molecule so that we can track where electrons actually are and where they're actually going. It's more convenient for us to talk in terms of whole numbers than it is for us to talk in terms of these partial numbers. And so that's why we call them oxidation states, because we're tracking electrons, but those oxidation states are written to look like actual charges when they're not actual charges. Notice you can tell the difference between an actual charge because it's written with the number and then the sign, versus an oxidation state that's written as the sign and then the number. Oxidation states are just convenient ways for us to track electrons, and it's more convenient for us to do that in whole numbers rather than partial numbers. And so we're going to assign those whole numbers as oxidation states. Okay, so let's take a look at those rules again. Remember, oxidation states, we're going to assign them according to some actual rules. And so the first couple rules are going to be actual charges. So, for example, if you're talking about a pure element has a balance of protons and electrons, and it has an actual charge of 0. And so we are going to assign an oxidation state that matches the actual charge of 0. This is true for any pure element, whether the element is monatomic, like iron, diatomic, like nitrogen, or something else like sulfur is S8, phosphorus is P4, ozone is O3. All of these are elemental states of these elements. And so each of the atoms inside of these elements are going to have an oxidation state of 0. Now, what do you have to know? Hopefully you're familiar with sulfur and phosphorus and ozone at this point in time, and you can recognize them as elements. But the only thing the test actually holds you accountable for are the monatomic elements and the 7 diatomic elements. Remember, the 7 diatomic elements make a 7 on the periodic table that starts with nitrogen and goes down to iodine. And then don't forget hydrogen. Okay, so those are your 7 diatomic molecules, and you should be able to recognize them as elements, which means they have an oxidation state of 0. Another oxidation state that reflects true charges are monatomic ions. So any monatomic ion, the oxidation state is just going to be equal to the charge. If it has a charge, we're going to use that charge as the oxidation state. And then a third oxidation state that reflects an actual charge is when the compound is charged. So if you have a whole compound, then everything inside that compound, all the oxidation states, the oxidation state of carbon, the oxidation state of the 4 hydrogens, the oxidation state of oxygen, they're all going to add up to the charge of the actual compound. So like methanol is a neutral compound. It's going to have an overall oxidation state of 0. Whereas on the other slide, when we were looking at, I think it was sulfate, the sulfur plus the 4 oxygens are going to add up to the charge of the actual molecule, which is a 2 minus. Okay, now we get over here to this side, and we start talking about oxidation states within molecules. So because we have a couple different atoms inside this molecule, we know they all add up to 0, but what are they inside the molecule? Well, for this, we use most common things. So like carbon, hydrogen, and oxygen, the most common charges are going to be carried by hydrogen and oxygen. Hydrogen in a compound is almost always 1 plus. The exception to that is if it's bonded with a metal. If it's a metal hydride, then the oxygen inside the metal hydride, the oxidation state is going to be a 1 minus. If you have oxygen, oxygen's another really common one. Oxygen is almost always a 2 minus. Now, that's true unless you have a strange form of oxygen like a peroxide or a super oxide. And then the charges of the oxygen within those ions will change a little bit based on the charge of the overall ion. But most of the oxygen that you come across is going to be normal oxygen. I mean, how often have we dealt with a peroxide and a superoxide? Never. We've never dealt with a superoxide. And only occasionally, I think we had one lab where we dealt with a peroxide ion. That was hydrogen peroxide. And the peroxide ion is going to be O2, 2 minus, and so each oxygen inside of that is going to have an oxidation state of a 1 minus. But unless you're dealing with a peroxide, oxygen is going to have an oxidation state of 2 minus. Okay, so just a recap. So you can see the forest and the trees. If we can use true charges, we will. Pure elements, monatomic ions, charges are going to equal oxidation states. Same thing with sum of ions in compounds and ions. The sum of all the oxidation states inside of those compounds or ions are going to be the actual charge on the compound or the ion. And then after that, we default to what is common. And our common things include hydrogen, almost always a +1, oxygen, almost always a -2, and then even things like alkali metals or halogens, those things are pretty consistent. +1s, -1s. If these things are going to change, then they're going to change because hydrogen and oxygen need to stay consistent. So this is kind of the ranking order. If you're going to figure out an alternate oxidation state for something, assign hydrogen first, assign oxygen second, assign alkali metals, halogens next, maybe alkaline earth metals would be next, and then figure out the other charges inside of those. So we did this extensively in the fall with chapter 4. I do have some practice here for you to go over. So we're going to go through this as a class. The exception to this is I do want to show you how things add up. So let me go through these two just as an example now, just to kind of jog your memory, and then we'll go through the rest of them as a class. So if we're looking at SO3, we know we have an S, and we have 3 oxygens, right? So the oxidation state on S, the 3 oxidation states on oxygen, they all have to add up to the charge of the molecule as a whole. And this one is uncharged, so they're all going to add up to 0. Now, which one do we assign an oxidation state to first? Well, oxygen is more consistent, so let's assign that one first. It's going to be a 2 minus, which means my sulfur needs to compensate for a 6 minus charge. I only have one of them, so sulfur must be a 6 plus charge. So each sulfur is going to have an oxidation state of 6 plus. Each oxygen will have an oxidation state of 2 minus, and together they're going to add up to 0. We can do this for ions as well. SO4 2 minus has 1 sulfur and 4 oxygens, and they have to add up to the charge, which is a 2 minus. Now, which one is going to be more consistent? The oxygen. So we'll assign oxygen's state first. That's a 2 minus, giving me an 8 minus charge overall. Now, what does sulfur have to be in order for the whole thing to add up to a 2 minus? It has to be a 6 plus. So sulfur in this case will have a 6 plus oxidation state. Each oxygen in this ion will have an oxidation state of 2 minus. Now, notice that the sulfurs both end up with a 6 plus charge. That's totally coincidence. Doesn't always happen. Sulfur will not always be a 6 plus. It's going to depend on what's around it and how those electrons are distributed. Notice also that both of these compounds are talking about covalent bonds, right? Sulfur is bonded to oxygen using covalent bonds, and even in the sulfate ion, sulfur is bonded to oxygen using covalent bonds. So we don't have true charges in here. These are not true charges. Sulfur does not have a charge of 6 plus, but there are electrons that are distributed throughout this molecule, and those are the electrons that are going to shift in a redox reaction. And so knowing it has an oxidation state of a 6 plus is going to help us to track those electrons as they shift. All right, so we will practice those other ones together in class. Hopefully this jogged your memory and it all comes back to you. Okay, we'll try this one in class as well. Now, how do you identify something as a redox reaction? Again, that's going to come down to the change in electrons. Remember, if it's a redox reaction, we're going to have electrons shifting from one thing to the other. It's not always super obvious. Sometimes it is really easy to see. We can see that iron's charge changes from a 3 plus to a 2 minus. Obviously, that's going to have to be because of a gain or a loss of electrons. In this case, if we're going from a 3 plus to a 2 minus, iron has gained 1 electron, right? So that one's pretty obvious. Of course, that's going to be a redox reaction. We have a gain, an obvious gain in electrons. Sometimes it's not so obvious, like in this example, all of these molecules are uncharged. Water is neutral, hydrogen is neutral, oxygen is neutral. So we don't have an obvious shifting of electrons. It's not obvious until we break it down and assign oxidation states. If we do that, then we see that we do have some changes. Let's take a look at this one down here. Again, not a super obvious redox reaction, but once we actually start to assign oxidation states, like silver is going to be a 1 plus because nitrate is a real ionic compound, or sorry, a real ion with a 1 minus charge. So these are actual ions inside of this compound. Silver has a true charge of a 1 plus, which means it's going to have an oxidation state of a 1. Well, over here, silver is in its elemental form, so it's going to have an oxidation state of a 0. Once we assign oxidation states, now you can see that the electrons are shifting. Silver, in this case, is going to gain an electron. So this must be a redox reaction. So some reactions are pretty obvious to see. Some reactions are not. Reactions that usually have that usually are redox reactions are single replacement reactions, like this one. Also combustion, or the opposite of combustion, which is what this is. This is the opposite of combustion. Those are also commonly redox reactions. Notice that this is also a single replacement reaction, and actually this is also a single replacement reaction. The only thing is the spectator ion has been removed. In this third reaction, we have nitrate is our spectator ion. And if we take nitrate away and we just write the net ionic equation, then it becomes a very obvious redox reaction. This is a 2 plus. So this one on top, this first reaction here, is a single replacement reaction. It just has its spectator ion removed. We can easily put in nitrate to this equation as a spectator ion, and we'll get something that looks more like this third reaction down here. Other reactions can be redox, synthesis, decomposition, double replacement. They can be, or they can not be. So you would have to check through oxidation states in that case. Okay, now these two terms are going to come up for you in your book, in review books, in lab, in industry, in reading about electrochemistry. You're going to hear these two terms, oxidizing agent and reducing agent. Now, these two terms are beyond the scope of our class. You are not actually held responsible for these two terms. They will not be used on the test. But since you're going to come in contact with them, I thought we might as well cover them. So the oxidizing agent is the thing that gets reduced, which is a little bit confusing. So if we go back to this one, oh shoot, what was it on the last page? Let's go look. And copper, we were using copper, okay. Okay, silver plus copper goes to silver plus copper as different ions. Okay, so for example, silver is going to go from a 1 plus to a 0, and that means it has gained electrons, so it is reduction. Well, if silver has been reduced, then it is the thing that is oxidizing copper. So silver is reduced, it is the oxidizing agent. Copper, on the other hand, is oxidized, which means it is the thing reducing silver. So copper is oxidized and it is the reducing agent. So it's a little confusing. If you hear these terms, you really have to stop and think about them. But it's good to be aware. You might want to just write this, write these definitions down so that if you come across it in literature, you at least have something to reference back to. But they will not be, they will not test you on these questions, on this terminology. And if you come across it in the book questions, you can skip those book questions. Okay, so we can practice oxidation states a little bit more on these reactions in class. But I want to talk a little bit more in this video about other things that we had talked about earlier in the year. So balancing redox reactions is something that we spent some time on in the fall. And we talked about how redox reactions are kind of special because not only do they need to be balanced in order to satisfy the conservation of mass, just like any other reaction, the number of atoms, aka mass, right? Mass in grams, on one side of the equation must be equal to the number of atoms and their mass on the second side of the equation. Basically, if you start with an atom, you're going to finish with that same atom. It might be rearranged and attached to something different, but it's still going to be there, right? So redox reactions have to be balanced in this way, just like every other reaction has to be balanced in this way, but they also have to be balanced in a special way. We also need to be sure that the number of electrons that we start with is also the number of electrons that we end with. You know, if something gives up 4 electrons, something else has to take on those 4 electrons. So when we balance redox equations, we have to make sure that the electrons are balanced as well. And this can be tricky to do. And so we talked about one method of doing this, which is the half reaction method. Now, because this is review, we're not going to spend a whole lot of time doing the half reaction method, but I do want to go through one example. Also, the half reactions method is not usually tested on the AP test. It's at least not tested extensively. There are a couple questions that ask you how many electrons are transferred or what's the coefficient. But because these problems take so long to do, the AP College Board doesn't spend a whole lot of time testing through them. So let's remember how to do this. Remember why we do this, just for the sake of coming full circle with redox equations. And then we're going to spend our time looking at some of the new stuff. Okay, so for example, remember as you use the half reactions method, there are specific steps you have to follow. So the first thing you want to do is to balance all elements except for hydrogen and oxygen. Again, we're coming back to this idea that hydrogens and oxygens provide a lot of the driving force for redox reactions. So you're going to balance everything except for those two. The second thing you do is you balance all oxygens by adding water, and you balance all hydrogens by adding the hydrogen ion. Now, can you switch these two steps? Well, if you add hydrogen ions first and balance all the hydrogens, then when you go to balance the oxygens and you add water, you're going to unbalance your hydrogens again. So then you're just going to have to return down and balance the hydrogens once more. So that's why you want to make sure you balance oxygens first and hydrogens second. Now, remember, we are doing this in a half reaction method. So the very first step, you're going to split the original equation into your two half reactions. And usually we do this by looking at all elements except for oxygen and hydrogen. So in the example that we've been looking at with copper and silver, in order to split the two reactions, you would take everything silver and put that in your first half reaction. And then you would take everything copper and put that in your second half reaction. So remember to do that first before you start going through all of these other steps. Now in this case, we don't have any oxygen or hydrogen, and so we would skip 2 and 3. When we're dealing with net ionic equations, this process of balancing becomes a lot more simplified. We really only have to go through this half reaction method when we're dealing with all the ions and all the molecules that are involved in these steps. All right, so after we have split the original equation, we've balanced the elements, the oxygens, the hydrogens, the next thing we have to do is balance the electric charge by adding electrons. So you're going to add electrons to each side of each half reaction so that the half reaction is electrically balanced. Like, for example, silver, the ion of silver and the element of silver, we have a 1 plus for the ion of silver and we have a 0 for the element of silver. These two things are not equal, so I'm going to add electrons in order to make them equal. I would add an electron to this side because it will add a 1 minus charge. And then my two sides are now equal. If I have a copper, oops, that should be a arrow, not a plus sign. If I have a copper and a copper 2 plus, again, my electric charges are not equal, and so I'm going to add 2 electrons in order to make both sides the same charge. So we add electrons in order to balance the electric charge, and then we're going to multiply the two equations to make that electric charge equal. So notice with silver, I only have 1 electron, right? In copper, I have 2 electrons. So if silver only gives off, no, if silver takes on 1 electron, that's not going to balance out what copper needs, right? And so we need to multiply both sides. So 2 silver ions, 2 electrons, 2 silver elements. And now silver will gain 2 electrons. Copper will give off 2 electrons. Now my electron transfer is balanced. And at this point in time, my elements are balanced, my electric charge is balanced. I can recombine these two into a full equation. So 2 silver plus 2 electrons plus copper goes to, actually, let me do it on the bottom. 2 silver ions plus 2 electrons plus copper goes to 2 silver atoms plus the copper ion plus 2 electrons. And notice in my equation I have electrons being transferred between one thing to the other thing. And so I don't actually have to include these electrons in the final equation. Since they show up on both sides, I can delete them and I get a final equation. Now notice if we were just balancing atoms up here, we never would have doubled the silver, right? It looks balanced. I have a silver, that looks balanced, a copper, that looks balanced. Unless we go through these steps, we never realize that my electrons are not balanced. So that's the purpose of the half reaction method, is to make sure not only are the atoms balanced, but the electrons are balanced as well. A good follow-up question to this would be how many electrons are transferred? Well, you can see silver absorbs 2 electrons, copper gives off 2 electrons. So 2 electrons are transferred between copper and silver. 2 electrons are transferred. Okay, so again, this is not a huge part of our curriculum. It's worth going through once. So this would be a good example. Go through it, see how far you get, and then we can come back and deal with it together as a class. You may also recall that you're going to have an additional step if you are balancing it in a basic solution. Normally we add H+, which is assuming that we're going to have an acidic solution. But some of these do happen in basic solutions, and if that's the case, you need to have one additional step where you add hydroxides to all of your hydrogens in order to take out the hydrogens, and you are either going to end up with water or hydroxides in solution, which would make it a basic solution. So again, after we talk about balancing that equation, we can talk about what that additional step is to balance it in a basic solution. Okay, here's more practice along with the answers if you would like a little bit more practice on balancing things using the half reactions method. And then this, I really like these pictures because it gets to the molecular level. So let's take a minute and look through these. Notice that in this case, you start with solid zinc. And you start with copper in solution. So notice here's the solid zinc. And then notice that the solution is blue, and that's because we have copper 2+ ions floating around the solution. And here you can see it on a molecular level. We have the solid zinc over here. And then notice we have lots and lots of water molecules, but we also have zinc molecules in here. And then this bulky molecule that you see once in a while is how the solution is acidified. So what happens as the reaction goes on and the reaction goes on to solid copper and zinc as an ion? Well, notice as zinc, let me change colors here. As the copper ions hit the solid zinc, they transfer electrons. Zinc is going to give electrons to copper. And when copper gains those electrons, it becomes elemental copper. And you can see that it becomes elemental copper and part of the solid. You can see that here with all of the different spikies that are sticking to our solid zinc. All of that is solid copper that is plating onto the zinc. Now, as the copper ion turns into solid, some of the zinc ion actually gets kicked out of the solution. So the zinc that gave up its electron gets kicked out into the solution. And that's what these little gray molecules are going to be. So the zinc that gave up its electrons falls off of the solid and becomes little particles inside the solution. And so inside this whole solution, you have zinc 2+ ions floating around. And notice it's clear, right? It's clear now because zinc 2+ ions are colorless. So I really love this drawing because it gets to what's happening on a molecular level instead of just on a mathematical level. So this is worth taking moments and maybe drawing out for yourself with a different reaction to really wrap your brain around this. Now, we talked about how redox reactions are an exchange of electrons, right? We have electrons flowing. In this case, we have electrons flowing from the solid zinc to the copper ions in solution at this border here where the copper ions in solution contact the solid zinc, right? Electrons flow. So the question we need to explore next is how do we get that to turn into electricity for us? You know, if you just screw a light bulb into this solution, you're not going to get it to turn on, right? Because the transfer of electrons is happening right here as the two molecules touch. So how can we separate that and force those electrons to flow through a wire? Well, that's the question of electrochemistry that we're going to explore here in a little bit. Okay, again, it's a great diagram molecularly that kind of breaks down what we were just talking about. The copper ions in solution are contacting zinc atoms in the solid state, and when they contact together, the electron is transferred. The copper is going to turn into elemental copper now that it has gained some electrons and is now solid. And the zinc, which has lost those electrons, falls off of the solid and goes into solution. So same concept, different image. Okay, so next time we talk together, we'll talk about how we can harness that electricity. We'll talk about that next time. The last thing I want to talk about today while we're together is the standard reduction potentials that we talked about again in the fall when we were talking about chapter 4. Okay, so this is our last piece of review that we need, and we will start here tomorrow. We will start with reviewing the standard reduction potentials, and then we will talk about how we can separate these reactions that are happening in order to force that electricity through a wire and harness the electricity. Okay, let me know what questions you have. I'll see you in class.